Good afternoon, everybody. Welcome to class. I do hope that we will not have the gremlins visiting again this week, that we can get through the business at hand. All right. I did invite you to look at the recording of this topic. I hope you did. But there are just a couple of things. I'm just going to run through quickly and then get to the fault analysis. All right. So I have reached the whole business zero sequence. And the key points I wanted to address here included the fact that zero sequence currents, and from the connections that I showed, the delta and the star and the grounded star, what we are saying is that zero sequence can only flow if there's a path to Earth. All right. So your zero sequence, simply put, can only flow if you have a path to Earth. When we consider the various connections for your delta, there's no connection to Earth, so there will be the zero sequence here would be equal to 0. Yes. Similarly, for your ungrounded star, okay, again, there's no path to Earth. So, as we said before, the zero sequence current, again, would be equal to 0. However, where we have a grounded star, then the impedance, or the zero sequence impedance, would be represented by your 3 times Zn, as we would have mentioned. So what we did was to look at the various components of your network that may have connection to Earth. So for your transformer, we have to take note of whether or not it's star or delta, but not only star or delta, grounded star, star or delta. There are other connections for your transformers, zigzag, such as zigzag, but we're not considering those connections. We are looking now at the star, grounded star, ungrounded star, and delta. Of course, for your grounded star, you can either ground it through an impedance, or you can have it solidly Earth, meaning from the star point, you are going directly to your Earth. So it is Earth through an impedance of 0, right? That's what we mean by solidly Earth. And then, of course, through an impedance, you're going through an impedance Zn. Then for your zero sequence, we would have your Z0 plus 3Zn. We also gave you a sort of, for use of a better word, a ready reckoner in terms of looking at the windings. And so we're saying that because your transformer will have 2 windings, yes? You have an input winding or your primary winding, you have an output winding or your secondary winding. One can be star, one can be delta, both can be delta. You have star, star, you have ungrounded star, star, you have grounded star, grounded star. So you have different combinations. And what we're saying is that for the contacts that we show in the network, we are going to close contact A if zero sequence can flow. And based on what we said earlier, you're only going to have zero sequence if and only if there's a grounded path or there's a path to ground from the star point. So you're only going to have that with grounded star connections. And then you close B if zero sequence cannot flow. So let us say for the network we have here, this is my zero sequence impedance. If zero sequence can flow, meaning if I have a grounded star on that winding, then I'll close A. If I have a star, so if this is a grounded star delta, then I would close B. So in other words, for the zero sequence impedance, you would have, all right? So you wouldn't have any connection to ground. And then you'll have that. Okay? So that's what the connection would look like. If, of course, I then have grounded star on both sides, then I would have this as my zero sequence impedance, all right? So in other words, I would have zero sequence current flowing. This, of course, would represent a solidly grounded star connection, yes? But if I earth it through an impedance, then we're saying you would add to this 3 times Zn, all right? So you'd have Z0, which is the zero sequence impedance of the transformer. But if you're earthing it through an impedance, then you would have 3Zn also connected in series, all right? For your transmission line, this is static, yes? So it means that Z1 is equal to Z2. So your positive and your negative impedances would be the same. And it's given by Zs minus Zm, where Zs here is a self-impedance, and Zm, the mutual impedance. These represent, for your transmission line, the self-impedance would be that of the line itself. The mutual would be as a result of the interaction between lines, okay? Similarly, for your zero sequence, it is Zs plus 2Zm. So what we have here is that your Z1, which is equal to your Z2, would be less than your Z0. So the zero sequence impedance for your line is larger than your positive and negative, but your positive and negative are always equal. Yes? All right. Then for your loads will be represented in a similar manner as the transformer, meaning you will have zero sequence only if you have a path for zero sequence currents, meaning that it is grounded. It's a grounded star. So for your loads, yes, here we have a star. So that point is open. If it's a solidly grounded star, then that's closed because we now have the zero sequence current able to flow. If we then have it through an impedance, again, we have the 3Zn. And for delta, you have a circulating zero sequence. Okay? And this is, well, I shouldn't say this, but one of the benefits, you will explore this in your fault analysis lab. You will look at the benefit of having a star delta transformer. You know, why do we connect them? And really and truly, simply put, it's just to separate or prevent zero sequence currents from moving from one point of the network to the next. So if we have a fault in a particular section of the network, when it comes to the delta winding of your transformer, then the zero sequence will not move across that path or that winding of the transformer to the rest of the network. So you're able to segment the network using your star delta as far as the flow of zero sequence is concerned. But as I said, you will explore that in a lot more detail in your fault lab. So having done that whirlwind review, you would have gotten a lot more detail from the video. Yep. We're not gonna just get into fault analysis, and we are slightly behind, but nothing to cause too much alarm. All right. So let us get cracking with what we have on today's agenda. So I want to look at fault analysis. Now, I want to start by looking at unsymmetrical faults. And why do we call them unsymmetrical faults? Or better yet, let us talk about symmetrical faults, and then it may be easier to understand why the faults that we're going to be looking at are referred to as symmetrical, unsymmetrical. A symmetrical fault simply means that all phases are impacted equally. All right. So if we had a fault where you had all three phases, A, B, and C, or red, yellow, blue, having are short-circuited simultaneously, then that would be a symmetrical fault because all phases would be impacted equally. So we can have them either short-circuited, they can be short-circuited to earth. That's still a symmetrical fault. An unsymmetrical fault, therefore, is where the fault does not impact all three phases equally. In other words, you may have one phase being affected, or you may have two phases being affected. Yes? So we have a phase to ground, or what we have before us, a line to ground. So you can have one of the lines, one of the phases, coming in contact with ground. It doesn't necessarily have to be that the line itself has somehow detached, become unattached, and falls to ground. That's not necessarily how that fault is created. You could simply have a tree that is, we're experiencing windy conditions, and the tree bends based on the wind, and a limb comes in contact with a line. Immediately you have a phase toward fault because the tree would, technically speaking, be creating a path from that one phase to ground. All right? So to do the analysis, we put forward what we refer to as boundary conditions. In other words, if I have one phase touching ground, what are some of the things that I can establish? What are some of the things that must be true? Yes? These are our boundary conditions. Fair enough? So if I have a phase, and usually in terms of the analysis, let's be clear, in terms of the analysis, we just assume that it is the A phase that is touching ground. Of course, that does not necessarily have to be the case, but we use the A phase for our analysis just to understand what is happening during such a fault. So for the A phase touching ground, so A to ground, the boundary conditions is that one, for the A phase going to ground, it means that VA must be equal to 0. In other words, because it is in contact with Earth, then it must assume the potential of Earth. And of course, we know that the potential at Earth is 0. So we know that VA must be equal to 0. The other thing we can say for a fact is that IB and IC relative to IA is equal to 0. In other words, if that phase A is experiencing a fault, then it means that the magnitude of that fault current would be significantly higher than the current that would have been going through B and C. So relative to the other two phases, the current through, relative to the faulted phase, which is the A phase, IB and IC are 0. All right? So these are our boundary conditions. So how do we use this information in terms of our analysis? So we remember these equations, all right? Remember these equations. Of course, we had not specified that IB and IC are equal to 0, but based on what we have here, based on the boundary conditions, remember, we are talking about the conditions that must exist during this fault. So what we know must exist is that IA is faulted. We don't know what that current is, but we know that VA would be equal to 0, and B and C, I, B and C are equal to 0. So we have now set them equal to 0. All right? Okay, are we finished with this? Yes, sir. All right, so if this is true, then if we simplify these equations, since these are both equal to 0, since IB is equal to IC, I can set those two expressions to be equal to each other. And from that, I0 would be eliminated, yes? So what we have left is that A squared I1 plus AI2 is equal to AI1 plus A squared I2. All right? I can bring the I1s together. I can bring the I2s together and factorize. And what we have is that A squared minus A is equal to I1, and A squared minus A times I2. A squared minus A I1 is equal to A squared minus A I2, regardless of what these are, this is equal to. What it implies, because these would be the same coefficients, it implies that I1 is equal to I2. So in other words, the positive sequence current is equal to the negative sequence current. And if I substitute this information back in equation 2, if I substitute into equation 2, ready again?
Yes, sir.
All right, if I make that substitution, then what we have is that I0 plus A squared plus AI1, right? Because remember what we had was I0 equal A squared I1 plus AI2, but of course I1 and I2 are equal, so I just put I1. Making that substitution means that 0 is equal to I0 minus 1. The question I suppose you're asking is, how did we get this to be equal to minus 1? I can tell you that 1 plus A squared is equal to 0. All right, so that's a relationship that you need to bear in mind. All right, you can test it in your own time. So A squared plus A would be equal to minus 1. So what we are seeing here from this expression is that I0 is equal to I1. So I0 is equal to I1, and we have already established that I2 is equal to I1. So simply put, I0 equal I1, which is equal to I2. And if I substitute this expression back, or this relationship, sorry, back into equation 1, because remember equation 1 just told us that IA was equal to I0 plus I1 plus I2. Yes? We had that IB and IC were equal to 0 based on the boundary conditions. So I0 being equal to I1 being equal to I2, if I substitute that into equation 1, then I'll get that IA is equal to 3 times I1. In other words, the faulted phase would have a current which is equal to 3 times the positive sequence current. So the big question for us is, how do I calculate this positive sequence current? And how we go about doing that is that based on all the representation that we started looking at last week, and I asked you to look at the video, and we wrapped up. We just mentioned it briefly here. If I0 is equal to I1 is equal to I2, and remember we started out by saying we needed to create equivalent circuits. That's where we started last week. We said we needed to create equivalent circuits, and this is about applying Fortescue's theorem. But in determining those equivalent circuits, we had to know how to represent the major components. So we have looked at how we represent the generator, positive, negative, and 0. We have looked at how you represent your transformer in terms of positive, negative, and 0. We have looked at a load. We have looked at transmission lines. Now, those are the 4 components, major components. And of course, loads can be static loads, can be rotating loads like, large motors. But those are the 4 major components that you're going to have in your power systems. Yes? You have your generator. You need a transformer to step up the voltage. You need your transmission lines to take it wherever you want to go. Then you have another transformer, and that transformer takes it into a load. The loads that we will be looking at for this module would not be individual loads like, as I just mentioned, a motor or, but we're looking at it from a transmission standpoint. So from the transmission standpoint, we'll be looking at all the load summed together and applied to a substation. So in the easiest example would be, since you have all been on campus before, and I'm absolutely sure you have all driven past the Hope substation. All right? So the Hope substation serves Hope Pastures, it serves Mona, parts of Garden Town, etc. So what we'll be looking at are all those areas summed together and presented as a load to the Hope substation. So those loads would be in the range of megawatts, which is what you would have seen in your labs so far. All right? So we are not looking at a single load like UTech or a single load like the hospital. We're looking at the sum of all these loads. All right, but I digress. Coming back to the fault, however, I0, I1, and I2 being equal, based on the simplified networks that we would have had, what this is telling us is that the 3 circuits would have been connected in series. Because we know, by definition, that components are connected in series, going back to your networks, if the current leaving the first is the same current entering the second, yes? So what we therefore have are, this is your positive sequence network, it's the equivalent network, yes? The equivalent negative sequence and the equivalent zero sequence. And note carefully, students, that the current for each are flowing outward, just as we had represented them earlier. All right, so we can't change that to suit our purposes. So the currents are flowing outward, yes, and they are in series. So they are equal because if we just look at the flow, we have I1, I2, I0, and it comes back around. All right, so that's the direction of flow. So I have not changed anything. All right, any questions? Any questions? Crystal clear. Oh, I like this. New dispensation. Oh, by the way, while I am on this, there are 3 students. If you're in the room, please, I'd like to meet with you after class. Mr. Bruce, Mr. Rose, and wow, Bruce, Rose, and who's the next person I need to speak to? All right, when I remember, I'll let you know. All right, so but those 2 I need to see. Let me see if I can pull up the information. Let's see now. All right. All right, so we move now to the next unsymmetrical fault that we oh yeah, and Gerard Ferguson. So that's Ferguson, Rose, and Bruce. If you're in the room, please meet with me immediately after class. All right? Okay, so we do the same, a similar analysis. First thing we want to do is to look at the boundary condition. So if I have, and for the line to line, the assumption it is B and C that are in contact with ground. So it's a B to C to ground. So based on what we just looked at for the line to ground, yes? Ms. Edwards, what do you think would be the boundary conditions here? Give me at least one. Edwards?
Yes, sir.
Go ahead. Tell me what you think would be the boundary conditions.
IA is equal to 0.
Speak up for me, please.
That IA would be equal to 0.
IA would be equal to 0. Okay, fair enough. All right, since you have got one right, carry on. What about the voltages? Based on what you saw for the first one.
Since IA would be equal to 0, D and DC in turn would be equal to 0.
I have my computer maximum volume, but I'm not hearing it clearly.
It's no fun, sorry. I'm saying since IA is equal to 0, then in turn BB and BC would then be equal to 0 as well.
BB would be equal to 0? Is that what you're saying?
Yes, sir.
You sure?
Yeah.
Huh?
Yes, sir.
VB. All right, fair enough. All right, so VB and VC would be equal to 0. Thank you, Ms. Edwards. All right, so this will be your boundary your boundary condition. So when we looked at symmetrical components, we also said that it is true for both current and voltage. So again, we can write our voltage equations, all right? And based on our boundary conditions, VB and VC are 0. Yes. And so we can do this similar analysis, setting them equal to each other. V0s disappear, or cancel rather, or not disappear. And so we're left with A squared minus A, V1 equal A squared minus A, V2. We're not interested what these actually equal to, but what we know is V1 is equal to V2. Yes? Now for the voltages, the analysis is not as simple as with the current. So if we add VB and VC, we know VB and C are equal to 0. So 0 plus 0 gives us back our 0. Yes? When we add them, we get 2V0, A squared A, V1 plus V2. But we already established that V1 is equal to V2. Yes? And we know that A squared plus A is minus 1. So we're using all of those relationships. It means, therefore, that, can I move on? All right.
Just a minute, sir. All right, sir. Good, sir.
Okay, then. All right. So 2V0 minus, of course, the minus 1 would be the A squared plus A. Yes? And we know V1 is equal to V2. So 2V0 would be equal to 2V1 or 2V2. So what that says to us is that V0 is equal to V1. Or in other words, V0 equal V1 equal V2. So again, this would come from our equivalent circuits, our equivalent positive, negative, and zero sequence networks. So Mr. Bailey, Omar Bailey, under what circumstances would the voltages all be equal to each other? How would we connect the networks to have the voltages being equal? So Bailey, where disappear to?
Over there, sir. Kind of lost.
Pardon?
Kind of lost or something.
Yeah, I'm asking, if you have three systems, how would they be connected for the voltages to be all equal to each other?
Following Kirchhoff principles.
Huh?
Follow Kirchhoff's.
All right. If we have three components and they are connected in a circuit, how would they be connected for you to be absolutely sure that the voltages across each of them is the same? How would they be connected?
Parallel.
I was still speaking to Mr. Bailey. Who is Black Dice? I have
Sorry
no
about
such
that.
I have no such person on my register, and I will remove Black Dice from the room in the next 30 seconds.
Sir Isaac is Anthony Merchant. Says a new laptop I using.
I don't
Sorry,
care
never
it is
realized.
who. I say adjust the name. All right.
All right.
Sir, would it? You hear me, sir?
So yes, Mr. Merchant, it is indeed that they would be in parallel. All right. So if you have a line to ground fault, the three networks are in series. If you have line to ground, then it means that they are in parallel. So the three networks would look like this. All right. So one of the common errors that students make, the three networks are connected in parallel, as shown. However, Mr. Harris,
Sir.
the three networks are shown in parallel, but what kind of circuit do we have? What kind of circuit are we showing here? Talk to me. Come on. What kind of circuit? Anybody? What kind of circuit do we have here?
So series parallel?
Series parallel. Thank you. So they are all connected. The networks are all connected in parallel, but we have a series parallel because the only component or the only equivalent circuit that has a source would be a positive sequence. So you have a positive. You have the source here, which means that the network or the circuit, the series parallel circuit. The next thing you need to take careful note of is that the currents. Remember when we were showing the equivalent circuits, we showed that the currents were all heading out. The currents in this instance are also going outward. So this is I1. So what does that mean with respect to I2 and I0?
So I1 would be I0.
So the current at I1 is different from I2 and I0, sir.
Yeah, we know they are different, but what else can we say? If we are maintaining the directions, the directions can't change.
Sir, that means I1, the sum of I1 and I2 is negative I0.
Well, you make me shake my head because I thought you were going there. But anyway, the sum of I2 and I0 is a negative of I1. Because I1 is coming here, and then it divides.
Sir, that's the same thing though, right, sir?
No, that's not what you said.
Sir, we say the sum of I1 and I2 is...
But you're saying the wrong thing again.
Negative I0, sir.
But you're saying the wrong thing again. And I'm saying to you that it is the sum of I2 and I0, which gives you the negative of I1.
Okay, sir.
All right? All right. So this is for your line to ground, or what we will say in many instances, a double line to ground fault. All right? The other option would be your line to line. So we now have two lines coming together. So if I have two lines coming together, anybody, based on what we have done so far, what would be the boundary conditions?
VB would equal to VC, sir.
All right, good.
And IB would equal to minus IC.
All right, thank you. So because the two lines are connected, you can only have one current flowing, yes? So IB would be going in the opposite direction of IC. So IB would be equal to minus IC, and VB would be equal to VC, because they're touching each other, so they must be at the same potential. We don't know what the potential is, but what we know is that they are equal. So the boundary conditions would be IB equal to minus IC, and VB is equal to VC. And so again, we start with our voltages. And remember now, unlike the first one, we don't know what the values of VB and VC, or the first two that we looked at. We don't know what VB and VC are equal to. All we know is that they are equal. So they are non-zero, but we don't know what the values are. Eh? But we can still equate them, because we know that they are equal to each other. So we can still equate the two expressions. So it will result in V1 being equal to V2. All right. So for the phase to earth, we looked at just the currents, in doing our analysis. For the phase to earth, or phase to ground, we looked at the voltages. And I suppose by now you get used to my network talk. We just go and, amp it up a bit. So for phase to phase, we're going to use both currents and voltages. So I've used the voltage relationships to show that V1 is equal to V2. And for the current, all right, that's IB, that's minus IC. And we equate them. If we equate them, what we have is 2I0 being equal to I1 plus I2. However, big question. What would I0 be equal to? Anybody? What would I0 be equal to?
I1 plus I2 divided by 2, sir.
I0 will be 0, sir.
Why?
Because there's no path to ground, sir.
And why is there no path to ground?
Because it's line to line.
All right. So there's no direct connection to ground. I know I was just harassing you a bit, but there's no direct connection to ground. So in other words, there's no path to go. So it would almost behave like an ungrounded star or a delta. Poor description, but I'm just using it in terms of providing reference. Yeah. So there's no path to ground. So I0 would be 0. So in other words, I1 would be equal to minus I2. So for your line to line, you have that VB is equal to VC. So if the two voltages are equal, what did I say? VB equal to VC? No, V1 is equal to V2. So for the equivalent circuits, for the voltages to be equal, what can you say about them? The networks. How are the networks connected?
They're parallel again.
They're in parallel. And for I1 to be equal to minus I2, what can we say here?
Most you can say both currents are flowing in the same direction.
But if they are in the same
Based on the
direction,
diagram.
no, but if they are flowing in the same direction, then I1 would be equal to I2.
Opposite.
Parallel.
So it remains parallel. Thank you, Mr. Grant.
All right.
Which is what we have here. Always bear in mind, Mr. Watson, that the currents are going out.
All right, sir.
So I1 would be equal to minus I2, and V1 is equal to V2. So for your line-to-line fault, there's no need to consider your zero sequence. And I might as well tell you, I've set questions like this where, you know, of course, in an exam, I'll tell students, one of the things you can rest assured is that I ask you to state any assumptions. So I will ask you for, I will give you the zero sequence information, but I ask you for line to line. The fact that I give you the information doesn't mean that you have to use it. All right, so in summary, because in terms of the theory, we're basically done with the theory, yeah? In summary, we want to look at the steps that you'll take for fault analysis, yes, using symmetrical networks. So step one, you will have your original network and you want to redraw it, replacing each component by its symmetrical equivalent. You would do that for the positive, the negative, and the zero sequence networks. Luckily for you, because you're not, because we are not specializing, so to speak, in power systems, you are doing, general electrical power systems rather than power systems analysis. All right. You would not, I am not requiring of you that you develop your own symmetrical networks. All right. But, generally speaking, your positive and negative sequence networks would look the same. The only difference is that for the positive sequence, you will have the source for your generator. All right. But in terms of the reactances, they would look the same. The values may not be the same because the negative and positive for your rotating systems, your generator and your motor would be different. Okay. But for your lines, your loads, your transformers, all those static systems, the positive and negative values are usually the same. Are the same. I shouldn't say usually, are the same. For your zero sequence network, the key here is that you would have to note for your transformer, whether the winding is a delta, a star, or a grounded star, and you would apply that AB connection principle that I went through earlier. And from those three networks, you then simplify and find the Thevenin equivalent at the fault point for each network. So in other words, depending on where the fault is on the network, you then look into those terminals. I remember all of those definitions. I mean, you have done Thevenin, so you're good by now. So you look into the fault point and determine the Thevenin equivalent at that point. So the only network that you would have a source in would be the positive sequence. The zero and the negative would all be reactances. So it's usually very simple. And this is where you would now apply all the principles that you would have learned in networks, whether it is, equivalent, converting delta to star, doing your series parallel, quickly writing your impedance equations. That's where these things would be important. Once you have those equivalent circuits, you then connect.
Sir?
Yes, Mr. Webby. Yes, Mr. Grant.
Yes, sir. I don't know if you budget out for everybody else, but you budget out for me.
Yes,
I didn't
sir, we
hear
lost you at one point.
anything at all, and I think that's
Come on, everybody.
one very, very important point that you just made, or you were about to make.
You serious?
Yes, sir. Could you repeat for us, please?
Well, I don't remember what I said. Anyway, I honestly don't, but let us see. So what I said is that you would have found the equivalent network for your positive, your negative, and your zero. The only difference between the positive and the negative is that the positive would have a source. You then find the Thevenin equivalent of each network. Yes. From the equivalent circuits, you then connect the networks based on the type of fault that you would be experiencing. So if you have a line to ground, as we just went through, you connect the three networks in series. If you had a line to ground, you'll connect them in parallel. If you had a line to line, then you'd put the positive and the negative in parallel. So that is point 3. I really hope I repeated what I had said before. Yes? The next step, we have this?
Yes, sir.
The next step is that you now calculate the per unit sequence currents, note, and why per unit? Because you would now not have the encumbrance of the transformer windings, yes? So everything is done in per unit. We don't know anything about actual units until we are finished. So you calculate the per unit sequence currents at the fault point or any other section of the network that is required. And here you would have used things like your current divider, voltage divider, you name it. All of those principles would now come into play. And once you have found your currents, you use your T matrix. Remember that T matrix, the 1, 1, 1, 1, 1, A squared, A squared, that beautiful, that midnight matrix. And you calculate the phase values. And then you convert the phase values, per unit phase values, to the actual values based on the base values that you would have had. So this, ladies and gentlemen, would be the process by which we do our fault analysis. All right. Now, this is a mouthful, and I certainly don't expect you to remember this offhand. But to help with the process, what we're going to be doing is just look at a simple example. All right. All right, so take this from it, please. Just so. All right, so I'll come back to this one just to explain what we're saying earlier. But for the question that we're going to go through, this is a circuit. All right, so because we're not asking you to do all of this analysis, all right, you have the question, so I'll just go through for someone who would be doing advanced, well, not advanced, but analysis, what they would have been required to do. All right, so let's start with our first circuit. For this circuit, we have our generator. Yes, we know that it is solidly grounded. For your transformer, we have a delta star, sorry. Again, solidly grounded. You look here, you have another one, delta star, or star delta. Here we have a star star. Here we have grounded star, grounded star. We have a grounded star, star. Good. Very important, because for these, it will help us in determining the zero sequence networks. So we'd have to take note of that. So for the positive sequence network, for this circuit, you would have your generator and the reactance. For your transformer, you would have another reactance. Then for the line, so here you'd have your line. You go into the other bus bar. Down here, you'd have your line, another line, and then you have your transformer and your generator. Okay? On the other side, let me just take that. I know. On the other side, you then have your transformer and your generator. The transformer and your generator.
Sir,
yes?
shouldn't there be another reactance down at the bottom? Where the generator 2 is.
All right. And you have this going to Earth. So the next question would be, where is the fault? So if we had our fault, let's say on this bus bar, we had our fault at that point. What we are saying is that you would find the equivalent the Thevenin equivalent looking into that fault point. So just as with your Thevenin equivalent, where you open circuit, we're saying you're looking into those terminals for your Thevenin equivalent. Okay? You'd use all those principles, but based on what your syllabus asks for, we're not going into that. But for persons who would do the analysis, they would have to go through all of this. All right? So this would be a positive sequence. And you would simplify it to your Thevenin equivalent, which would look something like this. So this network would be reduced to that, and that's your positive. Good. For your negative sequence, as I said before, the negative sequence would look just like your positive sequence. The only difference is that for your negative sequence, those will disappear. So that's your negative sequence. Again, you'll be looking into the fault point. So the only challenge really for your positive sequences, in an instance like this, it may be helpful that you convert this this section here, let's say that delta to a star. That would simplify your work. Yes? So you get that Y, so it would then connect to these two sections over here. Yep. Obviously, these two are in parallel. You simplify that, so you use your networks theories to simplify. For the zero sequence, however, let me for your zero sequence,
Sir,
yes.
there's a quick question.
Mm-hmm.
What if there's more than one fault in different sections of this? So
Very good question.
Would apply the same principles?
Meaning what?
Meaning, so what if we have where there's a line to line and one there was a line to ground?
You mean simultaneously?
Yes, sir.
Wow. Well, let us put it this way. Life can happen, eh? However, faults are so infrequent that the possibility of having two of them simultaneously is almost something that we have never really considered. And let me go further. Because in terms of a power system, for them to be happening simultaneously, for you to be forced to analyze them, it would have to be, they would have to occur at exactly the same time. Because your protection system works in milliseconds.
All right, sir.
You with me?
Yes, sir, I am.
So one fault would have to, when I say them acting at the same time, it would be, however, when I say same time, I mean exactly the same time. because the standard time to clear a fault would be somewhere in the region of about 400 milliseconds. So the impact of one fault versus another, it will be difficult to say, well, first of all, it is highly unlikely. It is highly unlikely, near impossible for you to have two faults occurring simultaneously. I mean, one fault, if uncleared, can escalate into a second fault.
Yes, sir.
But for both of them occurring simultaneously, it is highly unlikely. And escalation is something that has happened in Jamaica on more than one occasion. A couple of our last major blackouts have resulted from escalation. So you had a fault in a little pole somewhere in St. Catherine that was in a little swampy area. Leaned and created a single line to ground fault. And it wasn't cleared by the breaker because of lack of maintenance, and it escalated into a major bus fault and it collapsed the system, right? But in terms of analyzing faults occurring simultaneously, I would say it is not something that we need to consider based on how the power system itself operates.
Okay, sir.
But if you want to learn more, we can talk in January. All right.
All right, sir.
So coming back to the zero sequence, again, because it is zero sequence, we do not have any source. So we start with the generator. So for your generator, you would have just Z0, because the generator that we are seeing is solidly earthed. All right? Now, for your transformer, the primary winding there is delta. So A would be open and B would be closed. And then you have Z0 for your transformer. On the other side of the transformer, you have a grounded star. So A is closed. And then we come to the bus bar. For your line, we have that. Then down here we have that. Right. On the other side, we have a star. So A would be closed, so we'll get that reactance. But the other winding is our ungrounded star. So we'll go to Earth, all right? Well, it can go, no, from here. So here, all right? And then for your generator, you have that. For the transformer at the bottom, you then have your transformer. So A would be closed on either side because you have grounded star on either side. And then your generator. All right? And then down here, you'd have that. You have grounded star, then delta, and then your generator. So you'd have an open circuit here. And what this is showing you is that no zero sequence based on the fault on this bus. No zero sequence will be going to any other generators. Well, apart from this one over here, yes, because you have the delta winding or an ungrounded star. Okay? And so for this fault point, when you're looking in, yes, it means that that would be removed from the circuit, this would be removed from the circuit, that would be removed from the circuit. Okay? It requires Yes.
Yes, sir. Why would those be removed from the circuit? Because we're looking
Our
at the
open
fault at
circuit
that
right
point.
there. You have an open circuit right there.
Okay, I'm just making sure. Thanks, sir.
Okay. All right. So this is how you would go about doing this question. Yeah. For the next question, right?
Hold on, sir. 1 minute. How come it's not open circuit if it's grounded?
Huh?
Isn't it grounded? Isn't
What I
a
said.
grounded star?
Yeah, man. Note for this transformer, this one here, the winding, this winding is a grounded star. So it means that you would close A. So the remember that thing we told you about closing A and open B? So that's A closed. So you then close A and then you have the reactance. Yes? On the other winding, you have a star, ungrounded star. So it means that you're going to close B. So A would remain open, but B closed. So you end up with an open circuit here. So in other words, no zero sequence will be passing through this part of the winding or this part of the circuit, which is the generator, because it's broken by your ungrounded star winding.
Okay, sir. I have a question. Well, that is said. If you're looking at where a transformer one is, sir, I see we have a star and a delta collection. On one side, you have a delta, on the other side, you have a grounded star.
Yeah, man.
Would it be treated in the same way as how you did the transformer 3, meaning because the delta don't have any ground? Would that be an open source as well, sir?
Yeah, man. They will show that already. See it here?
Okay. Oh, okay. Okay.
It's also open. All right. But students, if you want the full excitement, then we talk in January. Right now, I'm just telling you what the approach will be. All right. So for the next circuit, which is a lot simpler, all right, we have all of this information. We'll get the data. So that's my network. We'll get the data sheet in terms of showing us all the various information. These are the values, the zero sequence values that you would get from the manufacturer. Note, of course, everything is in per unit. Your transformer information is in percentage. You have XN for T2. So we look at T2. Yes. So we're not showing the star and grounded star, but the mere fact that I tell you, yes, that XN, there's an XN, then you know it is a grounded star. So even if I didn't show you this, the mere fact that I give you an XN value means that you would have had a grounded star. Are you with me?
Yes, sir.
Good. So those are some of the things that I needed to bear in mind, but you won't go through any of these calculations. So I'm going to therefore say that you would then move ahead. You have the fault in the middle of the line. You're going to find the Thevenin equivalent circuit for the networks. So you draw the positive, you'll draw the negative, draw the zero. Then you determine the Thevenin equivalent, and then we do the rest of it. So where we are going, all right. So let me just quickly draw this. So we have zero, positive, that. All right. And then for the network, we have the transformer. So we have that. We have our line. We have our transformer, and then we have our load. The fault is in the middle of the line. So just to make life simpler, I'm just gonna put 2 reactances, all right, to represent half of the line. So the fault is here. So you'd be looking in here for the reactance. You with me? So what I'm going to ask you to do now, I'll send this question via Schoology. I don't need you to do any calculations. I just want you to draw the equivalent circuits. Yes? Just to draw the equivalent circuit. So you're going to draw, I've given you the positive. I want you to draw the negative and the 0. All right? That's all we're asking you to do.
Okay, sir.
So we'll come back to this. I'll come back to this, or I'll send you this information, but I really want you know to go to this question. This is what's going to wrap up our class for today. So take this question for me, please. All right. So we have the 3 networks, and we're asked to calculate the per unit current flowing into the fault. All right, so what's the first thing we need to take note of? So Clark. Marcel?
Yes, sir.
What's the first thing we need to take note of?
Yes, voltage A, B, and C.
Again?
Not quite sure.
Come on, just tell me what. All right, here's the question. What's the first thing you need to take note of? What is the most important thing you have there in the question? No? So Grant, what do you think? What's the most important bit of information you have there that you need to take note of? So Grant, you still with us?
Of course, sir.
Yeah, then answer me, man. Without that information, no make no sense we move forward. So what's the most important bit of information?
The line to ground fault.
Absolutely, the type of fault. So we need to know the type of fault. There's no point in us starting to move before we know the type of fault. All right? Why? It's because I am the one asking why you think it must have. So Mr. Duncan. So Duncan?
Yes, sir.
So we have a line to ground fault. So how do we, what does that tell us?
Well, based on what we did earlier in class, then we know how to connect these circuits that are given to us.
Okay, and how would we connect them?
We will do it in series.
In series, all right.
Yes.
So we have our 3 networks, and we now need to connect them in series. All right, so we have, that's my positive, this is my positive, it's my negative, here's my 0. All right. So we line them up and then we connect them in series. And in what direction must the current be going?
Out.
Out. Right? Doesn't matter if you want to put the current here. All right? Just know that it's going out. If you want to put it up top, no different. If that is going out, that's going out, it's going out, same thing. Okay? But since I've been putting them at the bottom, I will just maintain that. So you won't get confused. So we have here 1 per unit, J 0.15, 0.15, negative 0.0975. And J 0.057. All, of course, per unit. All right. And this is 1 PU. So, Mr. Freighter. Mr. Freighter?
Yes, sir.
All right, so based on what we have before us, what would I1 be equal to? What's I1 equal to? Come on, Mr. Freighter, man.
I1 is equal to the negative of.
We're going to negative, man. Let's look at the simple circuit now, Mr. Freighter. How are these items connected connected?
I1 is equal to I2.
Answer my question, man. I say, how are they connected?
Series, sir.
Huh?
Series.
I didn't get that.
They are connected in series.
Yeah, if I'm connected in series, will you come tell me about negative? No, there's not negative there. So if they're in series, how we find I1?
I1 is equal to I2 equal to.
Yeah, man, the theory, that's why they're in series, because I1 equal I2 equal I0. I'm asking you, look at the circuit you have before you, what is I1 equal to? Come on, Mr. Freighter. Miss Mundell. Are you in pain?
I'm here, sir. No.
You're groaning for. Come, I1. What's I1 equal to?
The voltage is a little bit different. I'm not certain.
Let me have to take back the passes from networks. Mr. Buchanan, what is I1 equal to? I see your hand, Mr. Clark. Yes, Buchanan.
All right, sir. I1 will be equal to EA divided by the sum of the impedances.
Will be equal to what?
EA divided by the sum of the impedances.
What is the EA? I have an EA there.
Oh, the positive sequence voltage,
which is what?
1 pu.
So it's 1 over J 0.15 plus 0.975 plus 0.057. Thank you, Mr. Buchanan. Mr. Freighter, work this out. So add up the 0.15, the 0.0975, and the 0.057, Mr. Freighter. Divide 1 by all of that. What do you get? Mr. Freighter, guy.
Sorry about that, sir. My calculator most of them for sir.
Look for calculator here in a power systems class.
Sir,
Yes,
I
Mr.
had
Grant. Yeah, Mr. Grant, you have up? Mr. Grant?
Negative J 30284.
Negative J, 3 what?
028.
No, no
How
number
much?
goes so, sir. There's no such number. Give me the answer again.
So negative 3.284.
Mr. Grant was speaking, Mr. Wilson. Go again, Mr. Grant.
Negative J 3.028.
Oh, 3.0. Okay.
Yes, sir.
Yeah. So 3 point, oh. I don't know where this thing goes.
How much figures you
3.0
want?
what?
28.
Sir, we actually get 3.284.
It's
3.284?
3.2. Yes, sir. 3.2, not 30.
0.07.
3.2. Is that Grant? Go ahead, sir. Hope to 3.2 what?
84.
All right, thank you.
8407.
And what's the unit, Mr. Morrison? So Morrison? All right. Mr. Darby, what's the unit?
Ampere, sir.
Mr. Campbell, what's the unit?
IPU.
Huh?
IPU.
IPU, what name, sir?
Per unit.
Oh, so it's PU.
Yes, sir.
IPU, you know. So it's 3.284 per unit. All right. Now, what were you asked to calculate? You were asked to calculate the per unit current flowing into the fault. So what we're saying is that these equivalent circuits, these are the circuits that you would see at the fault point, all right? So you see them at the fault point. So from this, we need to find the current, the per unit current. But what does this represent? What does I1 represent? Mr. Perkins, what does I1 represent?
The current in the positive sequence. Sorry, the positive sequence current.
Positive sequence current. And what are we asked to calculate?
The current flowing into the fault.
Which would be what?
That would be the negative J 3.284 per unit.
No. Anybody want to answer that? What are we really being asked to calculate?
Sir, the zero sequence, sir.
Come on, you're guessing. You're not thinking. Miss Lynch? When I ask you to calculate the per unit current flowing into the fault, what exactly are you being asked for?
Sir?
What exactly are you being asked to calculate when you're asked to find the per unit current flowing into the fault? What we have here is I1. I1 is a positive sequence current. What are we being asked to calculate? Yes, Mr. O.
Is it the zero sequence current,
No,
sir?
no. Zero sequence is just, positive sequence, zero sequence, they're
Okay.
part of the theory. But I want to know the per unit current that is flowing into the fault. So what exactly am I being asked to calculate?
The current in the network at the time of the fault, sir.
Which would be what?
Overall.
The phase current?
The phase currents. Thank you. So I'm being asked to find IA, IB, and IC.
All right, sir.
Remember, the positive and negative sequence currents are a means to an end. They are the in-phase currents that we are going to add in order to get the actual phase currents. You remember Fortescue's theorem that we spoke about last week?
Yes, sir.
Good. So remember I told you to keep the T matrix in your calculator. So IA, BC would be equal to, all right, oh, Ms. Kamak, give me the T matrix. Kamak, T matrix, please.
Sir, it would be 1, 1, 1 A square A and 1 A square.
Yeah.
Times by the I1, I2, and I3.
Hmm?
No, hold on, sir. It be times by IA, IB, and IC.
But may I have that at the front already?
Sorry.
Well, you need to remove those distractions from you, from around you,
Sorry.
and try and focus. All right, thank you. Okay, so we know that I0 is equal to I1 is equal to I2. Yes? So if they are all equal, by the way, it's a face to earth fault, eh? The face to ground fault. So if without calculating, without using our T matrix, what would IA be equal to?
3 times I, sir.
3
times I1.
3 times I1.
3 times I1. All right, so you can use the T matrix. As I said, I hope you have it stored in your calculator, so you don't have to keep putting it in. That does take a little time. Yeah. So IA would be equal to 3I1, which is equal to
9.8522 at angle minus 90.
okay. All right. So minus J, which is 9.855522 at 90. And this is per unit. All right. So remember, they asked for the per unit current. And that is what we have there. What if I asked you for the fault current that was flowing? What if it was a fault current that we needed?
Would not be just IA, sir.
By the way, based on what we have here, when I calculate IB and IC, what would they be equal to?
0, sir.
0. Right? Because remember, everything over this matrix, everything is equal. And 1 plus a squared plus a is equal to 0. We had said that earlier, all right? Okay, good. So if I wanted the actual current, what would I need to do?
So would need a base.
We need a base current. How do we find that? What's the base current?
The per unit current.
How do we find the base current? First of all, what's the base voltage that we'd use for this question?
The 1 per unit, sir.
Base voltage. What would be the base voltage?
Sir, about 69 kV.
Huh?
69 kV.
Why?
Sir, that's the value that is used, sir, out here.
I don't know what you mean by that out here. Miss Lynch, where's Miss Lynch? Miss Lynch, not here. So she don't know what you're talking about. So what's it? Why is 69?
So that is the value that we distributed, sir.
Why are you telling me out here and this is what? Why are you choosing 69? You tell me 69, all right, I will accept it, but I need a reason.
Sir, I believe because it's on the secondary side of the
No, sir. No.
Sir.
Sir, because you're speaking about the transmission line, and that is the voltage on the transmission line.
Thank you very much, Mr. Darby. The question tells you that the fault is on the Jamaica transmission network. So therefore, I expect you to choose either 69 kV or 138 kV. So if I see that everybody in the exam going to choose 69, then we know something is up. You understand me? Are we clear? So you go and choose it. That's why all my exam papers say what? Clearly state your assumptions. So don't just tell me 69. I need to know why. The question tells you clearly the fault is on the transmission network. So it means that you're going to choose one of the transmission voltages. Students, nothing I say must be ignored, okay? All right. So what would be the S base? What's S base? Come on, man. You only have 10 minutes left, you know. What would be S base?
100 MVA, sir.
100.
All right, anything. 100, 150, 200. You go and choose it, right? Fair enough? Because it's arbitrarily chosen. Of course, you're not going to choose 10 because that is much too small, no? So I base is equal to S base root 3 V base, yes? And so once you have I base, you multiply it by your 9.8522, and that gives you what unit will the current be in when you calculate it?
Kiloamps.
Kiloamperes. Any questions? All right. So part 2 now says, what are the phase voltages at the fault point? So so you asked for the phase voltages. So what do we want?
And the voltage at each sequence.
Go again?
Need the voltage at each sequence, a positive sequence, zero sequence, and the negative sequence.
All right, no. So we'll be, and the rest there. Anytime we speak about phase voltages, or we simply say voltages, what we are seeking are the A, B, and C. Are we clear? If we want anything else, we will specify. So if we're asking you for the positive sequence, we'll say positive sequence. If we want negative, we'll say that. But if we ask for voltages, because remember, the positive and negative sequence are a means to an end. What you're going to be measuring, what you're going to be measuring are the voltages on the phase.
Yes, sir.
A, B, and C. All right? So we want A, B, and C. So I want VA, VB, and VC. How do I go about determining VA, B, and C?
So would we clearly state based on what you are giving us that VA is already equal to 0?
Again?
VA is equal to 0 because it's a boundary condition that you have given us.
Yeah, man, but you can't start there, Mr. Wilson. I'm not disputing that. You're correct. But how do we go about finding these three voltages?
So how do we put the 1/3 T matrix?
No, but the 1/3, that is the inverse of the matrix, eh? That is when you're trying to find the sequence values, the positive, negative, and 0.
Sir, would it be the T matrix times VA0, VA1, and VA2?
Thank you very much. So it is T times 0, 1, 2. All right? So the big question now is, how do I find 0, 1, 2? How do I go about finding that?
From what I had said first.
Which is?
The circuits, the different circuits for the positive, negative, and 0.
Excellent. So we'll go back to these circuits. You now know what I1 is equal to, all right? Which is also equal to I2. Yes? Which is also equal to I0. So what is V1 equal to? Remember, in class last week, we looked at, this would be V1. You remember that?
Yes, sir.
That's V2, and that's V0. All right? So what is V1 equal to? Just give me the expression.
V1 equal to 1 minus I1 Z1, sir.
V2, now V2?
0 minus I2 Z2.
And of course, V0 is 0 minus I0 Z0. And you put those in your equation, and you find ABC. And what units would we have here for VA, B, and C?
KV, sorry, KV.
Again?
Per unit.
Per unit. So the result here would be in per unit. But what did we ask for? We asked for the phase voltages. So the phase voltages must be the actual values. So based on the selection that we did for VBase. Once we have gotten VABC, we'd multiply that by the base voltage in order to get the actual.
All right, sir.
Any questions?
Sir, could you please repeat that?
The answer you get is in per unit, so you convert the per unit to the actual by using the base values or the base voltage that you would have selected.
Okay, sir, thank you.
You're most welcome, sir. All right. So the third part of the question now asks that it says, assuming that these same networks resulted from a double line to ground fault. A question, would the networks be different based on the type of fault? What do you believe would cause the equivalent networks to be different? Come on, want to talk to me? Why you don't want to talk to me?
Because one of them is because one has a positive and one is a negative
No,
sequence.
I don't want you guessing. You're guessing.
No.
You're guessing. I know you're guessing.
No, sir. You say what we call them to be different.
What would cause the equivalent networks to be different?
Sir, I think the only thing that will cause a difference is if the fault occurred in a different location.
Absolutely, Mr. Allman. Perfect. That's the only reason. That's the only basis on which the equivalent networks will be different. If the fault is located in a different point on the network. I hope you all write that down. But anyway, moving right along. At least Mr. Allman knows, so I'm good for mid-session now. All right. Now that we have a double line fault, that's what we asked for, no? So it's now a double line to ground fault. What will change? What is it that will change?
So it won't be in series, it will be in parallel.
Thank you. So they will be in parallel. So for the networks, we'll now have the same networks connected in parallel. Again, currents going out. That's I1, I2, and I3. So, just a hint, in finding I2 and I3, you'll be using current divider, yeah? But bear in mind that that will be the negative of those two currents. All right, students. I just have a few minutes to do this. So, all right. So it's 6 o'clock. So here is my task for you. This last question that we have just gone through, you're going to, we have gone through the solution, right? Apart from part C, I've gone through everything else. You're going to rewrite the solution that we just went through for this last question. Rewrite it properly, making your statements. We have said all that you need to state. You're going to go through it and rewrite it properly. And you're going to upload that to the system. I give you until tomorrow morning to do that. Oh, that's all. 30 minutes to rewrite it. You have the answers already. Yes, I give you until tomorrow morning.
Right through to part C. sir.
Huh?
Right through to part C.
Yeah, man, everything. A, B, and parts A, B, and C.
Plus the other network where we're to.
No. Just. Oh, yes, plus that one. Yes.
Yo.
Oh, it's all right. I wouldn't have forgot, Mr. Hope. It's all right. No, don't blame me. Because I already said it. Just listen to your names, eh? Alan, Romario. All right. Alman is here. Bailey is here. Brown, Garrett Brown.
Yes, sir.
Bruce.
Here, sir.
Oh, Mr. Bruce, stay on the line.
Yes, sir.
Buchanan.
Here, sir.
Bosu. Him gone? Tara? All right. Where is here?
Yes, sir. Yes, sir.
Come on, answer fast, man. Kamok.
Yes, sir.
Campbell.
Here.
Chambers.
Yes, sir.
Chen.
Here, sir.
Clark.
Here, sir.
Daly.
Yes, sir.
Darby. Duncan. Edwards. Ferguson. So Ferguson, you would be surprised. You're going to miss out on, but anyway. Ferran.
Yes, sir.
Ferran.
Yes, sir.
Forrester did say he was going to be absent. Freighter.
Yes, sir. I'm here.
Grant.
Yes, sir.
Gray. Green. Paul.
Present, sir.
Harris.
Present, sir.
Harvey. Harvey.
Here, sir.
George. Henry.
Yes, sir.
Henry. Zavina.
Here, sir.
Hope.
Here in one piece.
Johnson. Antonio.
Yes, sir.
King. Christopher. Miss Lynch.
Present, sir.
Mason.
Yes, sir.
Merchant.
Yes, sir. Yes, sir.
Morrison.
Yes, sir.
Mundell.
Here, sir.
Perkins.
Here, sir.
Porter. Tyreek.
Here.
Ready. Reed. Christoph.
Present, sir.
Rose. Shand.
Here, sir.
Thomas.
Here, sir.
Turner.
Yes, sir.
Watson. Danica. Or Danikia. Watson. Nikolai. Nikolai gone? All right. Wilby. Williams.
Here.
Williams.
Here, sir.
And we'll be here, sir.
And Wilson.
Here, sir.
All right. Okay, so Mr. Bruce. All right, so have a good one. I'll put up the link in a few minutes.
Okay, sir. Have a good evening.
All right, take care.
Yes, sir.
Mr. Dr. I had sent a message on school that did you get a chance to read it? Hello?
Yeah, man, I hear you. Just wait a sec. Come, folks, log off quickly for me.
Sir, you're still recording here.
Sir, I didn't